All right, here's an introductory video for section 5.2. We'll start with the warm-up and just look at some different functions. We'll look at them as graphs and we'll look at them as equations and think about their end behavior. So if I have, and these functions are not the same as the ones in the warm-up, I'm just making them up off the top of my head. If I have a function that looks like 3x to the fifth minus x squared, x to the fifth is going to dominate when I get big, and that basically looks like an x cubed, right? Because our x cubed function comes through like this. And so an x to the fifth is also going to look more or less like that because that coefficient is positive. So I would say as x goes to positive infinity, f of x goes to positive infinity. And as x goes to negative infinity, f of x goes to negative infinity. There's one. Here's another example, minus 2x to the fourth plus 7x. And here I say, okay, it's x to the fourth, so it's going to basically look like a quadratic, an x squared when we get really big, but they're negative, so it needs to come down like this. And that tells me that as x goes to positive infinity, g of x goes to negative infinity down here, right? X goes to positive infinity, y goes to negative infinity. And as x goes to negative infinity, g of x goes to negative infinity. X goes to negative infinity down here, and the outputs also go to negative infinity. Let's look at another one. How about something factored? 3 times x minus 2 to the fourth times x plus 1 cubed times x minus 4 squared. All right, and I start by saying, okay, I need to know what the leading term of this polynomial would be. I know by looking at the factors, since there's ones in front of all the x's, that 3 is my leading term. And to find out the power on the x, I say it's x to the fourth times x cubed times x squared. 4 plus 3 plus 2 is 9. And then I have other terms. And those terms are important for my interior behavior, but they don't matter for my exterior behavior. And so once again, just like the function that we started with, the f of x, this one is going to have behavior that looks like that. There are a couple more on the warm-up, and now you can work through those. All right, so that's end behavior. Still working on the warm-up. Let's look at multiplicity. All right, so start with a graph of just a simple function, y equals x plus 3. All right, and even though I wrote the y-intercept down there to help me graph it, what we're going to focus on is this place right here where it crosses the x-axis. And we see that is linear because my function is linear. So this 0 has a multiplicity of 1. In particular, the actual 0 is x is minus 3 and y is 0. That's my x-intercept. So that's your basic y equals x plus 3, a multiplicity of 1. I can also look at multiplicity of 2. So I could look at something like x plus 4 squared, or maybe two different factors. X minus 5 times, nope, let's just do that, x minus 5 squared. And x plus 2, or x plus 4 squared is a quadratic that touches right here at -4, 0. And when you zoom in, You see that looks quadratic. It touches and then bounces off. When x minus 5, I don't like that one. I'm going to do a different one. Instead of the power of 2, I'm going to raise it to the power of 4. Basically, there's my 0.50. It still looks like a quadratic, but maybe it flattens out a little bit more right here. So when you zoom in, it still basically looks quadratic. It bounces off. And a multiplicity of 2, 4, even, etc. So a multiplicity of 3, 5, odd, etc. I could have x plus 1 cubed. There's the point -1, 0. And my function comes up like so. And so we can see it crosses, but when we put a window around it, it's a little harder to draw cubes, but you should see that it's flattening out right as it crosses and then goes up. Or I could have x minus 2, I'll put a negative out in front, to the 5th. So there's 2, 0. It's negative, so it's going down, but it's still going to flatten out right as it crosses. And so when you zoom in, you can still tell that it's flattening out. So those are the 3 types of multiplicities we're going to be concerned with. We're going to be concerned with ones that have a multiplicity of 1, so it looks totally straight or mostly straight as it crosses. An even multiplicity, so it looks like a quadratic and bounces off. Or an odd multiplicity of 3 or greater, so it looks like a cubic as it kind of goes up. I think of this sometimes as a waterfall. Looks like a waterfall as it crosses. All right. That was the warm-up. With that warm-up out of the way, let's do the summary box. So this is the workbook section. And for the summary box, I'm going to use an example function. I'm going to say 3 times x minus 1 times x plus 2 squared times x minus 4 to the 5th. Because I think it will help as we fill things out. Okay, so this has a multiplicity of 1. This is on page 121, by the way. Multiplicity of 1. This is an even multiplicity. And this is odd multiplicity greater than 1. So first of all, if we know the multiplicity is 1, the least possible multiplicity just also is 1. With an even, I mean, my multiplicity could be 2 or 4 or 6 or 8, but the least possible it could be is 2. And with an odd that's greater than 1, it could be 3 or 5 or 7 or 9, but the least possible is 3. And the reason we ask about this is sometimes we'll give you a graph and we'll ask you what's the least possible multiplicity. The 0 will always just look like x equals, or I'm going to say the root, and you'll understand, x equals r. It doesn't matter if it's a multiplicity 1, a multiplicity 2, or a multiplicity 3. So in this case, if I look at my multiplicity of 1, my 0 is x equals 1. Here, if I look at my multiplicity of 2, it's still just written as x equals r, just whatever that root is. And in this case, it's x equals -2. And here for my odd multiplicity, it's still just written as x equals r. And in this case, it's x equals -4. Where things start to change a little bit is what the factors look like. So when we have a when we have a factor of multiplicity 1, we just write it as the factor. When we have a factor of an even multiplicity, so there's our factor, in this case x plus 2 squared, and x minus 4 to the 5th. So to recap, the root is the number that makes it 0. The factor is the term you see in the formula. And then the x-intercept is just the way you would write this as a coordinate pair. X is 1, that makes y 0. Or if x is 2, that makes, if x is negative 2, that makes y 0. And if x is 4, that makes y 0. So that's that summary box. Then we're doing some matching of polynomial functions with the graph. And so I'm not going to do matching, but I'll just pick a polynomial function and we'll talk about how to figure out what that graph is. And then you use the same techniques for matching. So let's say I have a basic x plus 2 times x minus 3 squared. And I want to know what to expect. Well, the first thing to do is to look at my factors and figure out the roots. There's going to be a root at minus 2, and there's going to be a root at positive 3. The next thing to do, so 1, find the roots. 2 is determine the leading coefficient. In this case, my leading coefficient is just 1. Once you have this information, and in particular the leading coefficient, and then 3, the degree of the polynomial, you can figure out what my graph is going to do. So this is a leading coefficient equals 1, degree equals 3. So I know it's going to have n behavior that does that. Because it's a cubic, overall it's got a degree of 3, and it has a positive leading coefficient. Now I'm going to find the multiplicity of each root. So for my root at x equals minus 2, the power on there is 1, so this has a multiplicity of 1. And for x equals 3, the power is 2, so this has a multiplicity of 2. That means when I trace my graph, multiplicity of 1 means it has to cut straight through, just like the line. And a multiplicity of 2 means it has to bounce off like a quadratic. And notice, since it starts down to the left and it cuts up, in order to touch that second 0 and end up, it does have to bounce off. So all these different parts all agree with each other. The multiplicity of each root, the degree of the polynomial, and the leading coefficient all work together to show you what that graph should look like. All right. I'm going to leave that up there just as a comparison. So if I take another function that's going to look similar because it's going to have the same roots, it's going to be x plus 2 to the 4th times x minus 3 cubed. Still has the same roots at x equals minus 2 and x equals positive 3. The leading coefficient is still 1. The degree of the polynomial is 7. So I know the end behavior is going to be like this. And now I need the multiplicity of each root. So here's my -2, here's my +3. Now the multiplicity here is 4, and the multiplicity here is 3. And that means when I start down to the left, when I touch this one, I have to bounce off because it's an even multiplicity. And then when I cross through here, I have to flatten out because it's an odd multiplicity that's greater than 1. And so if you pause this video and you compare the two graphs, there it is. If you compare the two graphs with their two formulas, you should be able to match the way the graph behaves at the 0 with the multiplicity of that root, of that 0, in both this graph and this graph. All right, so we got some practice doing leading coefficients and degrees and end behaviors and multiplicity, and that's going to carry us all the way through question 6. So let's move on now to 5.2, question 7. And again, this is a similar question, but maybe not the exact same question. So if I have a function f of x that's, let's say, minus x to the 5th, plus, I'm going to pause the recording so I can think of the question. Okay, I'm back. Minus x to the 5th plus 3x to the 4th plus 10x, or sorry, plus 10x cubed. Minus x, I'll just write that again. Minus x to the 5th plus 3x to the 4th plus 10x cubed is my polynomial f of x. So the first thing you should notice is we don't know how to factor polynomials of degree 5. We don't have the tools to factor polynomials that are greater than degree 2. So there must be something going on. So don't panic if you see a 5th degree and you're asked to factor. What that probably means is that you can do a little bit of analysis of the function and realize that's an x to the 5th, that's an x to the 4th, and an x cubed. I could pull an x cubed out of the whole thing. X cubed times x squared is x to the 5th. X cubed times x squared is x to the, that should be 1. X cubed times x is x to the 4th, and x cubed times 10 is x cubed. And then I'm also going to pull that negative out because I want my leading coefficient in front of everything. And I do know how to factor a quadratic. In this case, it's, that should be, I'm going to have to start over because I made an error. So let's try this again. Rewind into where we see this original function, and then factor out the x cubed. And now I'm going to factor out the minus sign. So I put the minus in front, the negative x squared becomes positive, the 3x becomes minus 3x, and the 10 becomes minus 10. And this I can factor because I chose it so that I could. That's x minus 5 and x plus 2. And that should be an x cubed. And now I have a polynomial written in factored form. So again, to recap, if you see a polynomial that's degree 3 or degree 4 or degree 5, and you're asked to factor it, probably you can pull out enough x's to get it down to a quadratic and factor it. And so now we can make a graph. We'll start by finding the zeros. Well, x equals 0 would make the whole function 0. x equals 5 would make the function 0, and x equals -2 would make the function 0. There's my point 0, there's my point -2, and there's my point 5. This is what's my total degree. Well, I could add them up, or I could go back to my original, which is a 5th degree, and it's a negative leading coefficient. So I know it's going to end up looking like that, like a waterfall going down, because it's a negative leading coefficient and degree is 5. So now I just have to check my multiplicities. My multiplicity at x equals -2 is 1. So it comes down and cuts through. My multiplicity at x equals 0 is 3, so it should flatten out. And my multiplicity at x equals 5 is 1, so it should cut through. And that allows me to check my end behavior. Yes, it started up and to the left, and it ended down and to the right. One more piece for this, which is solving a polynomial inequality. Sometimes we want to know not just when my function is equal to 0, but I might want to know when my function is greater than 0 or less than 0. So when is this function f of x greater than 0? So what I'm going to do is I'm going to look at my graph, and I'm going to say, okay, I need all the x values where my graph is up here. And that's when my polynomial is greater than 0. And I notice that the cut points on my interval are right at my zeros. So when is a polynomial greater than 0? Between the roots. So in this case, I can just plot those roots in a number line. So it's greater than 0 all the way back at -infinity until I get to -2. But then it's less than 0 until I get to 0, and then it goes back above until I get to 5. So solving a polynomial inequality by graphing, as long as you're asking about when is it positive or when is it negative, is just finding those roots and then seeing when your graph is in that shaded area. All right, lots more information in this chapter. So let's move on. 5.2, question 8. So so far we've taken a formula or an equation and tried to make a graph. And now we're going to take a graph and try to understand what the formula might look like. All right, so let's say I have this function here. Let's say that is -4, that is -1, that's 1, and that's 3. And just for fun, let's say that point is -1 right there. Okay. So I need a possible equation for this function. There's a whole bunch of information I don't know, but there is some information I do know right ahead, which is what the roots are. So I'm going to put those roots in as different factors, and then later I'll add the multiplicity. I know that if x equals -4, or if x equals -1, or if x equals +1, or if x equals 3, I'm going to have 0, so I can write those factors in. So the factor that goes along with x equals -4 is x plus 4, x equals -1 is x plus 1, x equals 1 is x minus 1, and x minus 3. And now I'll look at the multiplicities. That looks like it cut straight through, so that's a multiplicity of 1. That bounces off. So it could be a multiplicity of 2, it could be a multiplicity of 4, could be a multiplicity of 6, but I'm going to keep it simple and do 2. That one flattens out, so I'm going to say it's a multiplicity of 3, and that one bounces off, so I'm going to keep it simple and say it's a multiplicity of 2. And then the last thing to do is check my end behavior. It's going up on both ends. In particular, it's going up when x is positive. So the leading coefficient should be something positive, maybe 2. And so my formula, to write it all in one color to make it simple, if this function is f of x, a possible formula would be 2 times x plus 4 times x plus 1 squared times x minus 1 cubed times x minus 3 squared. And so we got all of that information from the graph. The last thing we can do is suppose I want the actual leading coefficient and not just a possible leading coefficient. Right, so instead of 2, I want what it actually is. In that case, I can solve for it because I've got this point -1, 0, which is going to help me. So if you think back to finding the equation of a line, if you have the slope, you just need one more point in order to figure out the rest of your equation. With a polynomial, if you have all the factors, you just need one more point to figure out the leading coefficient. I'll write that down. The polynomial, if you know all the factors, you need just one more point to determine the leading coefficient. And here's how you do it. Instead of a 2, I'm going to write in another number, just a placeholder. I'll call it A. And so I don't know exactly what A is. I think A is positive, but we'll find out. Even if I get it wrong in this guess, I'll get the right one here. I have one more point, and that point is the y-intercept, which is 0, -1. That tells me that if I put 0 into my function, I'm going to get -1 out. And here's my function. So if I put 0 into my function, I get -1 out. That's x, or A, times 4 times 1 squared times -1 cubed times -3 squared, because I've replaced the x with a 0 in every spot. Now it's arithmetic. 4 times 1 is 1. That's -1. That's +9. So 4 times -1 times +9 is -36. So A must equal 1 over 36. -1 over -36, or 1 over 36. That's positive, like I thought it would be because of my end behavior. And so when I'm all done, my formula equals is going to be 1 over 36 times x plus 4 times x plus 1 squared times x minus 1 cubed times x minus 3 squared. All right. I'm very aware that this video is taking long, but I think it's worth doing it again, or doing another example. I'll make a simpler example this time. All right, let's say that's -2 and that's +1. Instead of picking my y-intercept, I'm just going to pick some random point, like here. I'm going to say that point is 2, 5. Okay, so what do I know about my function? I know what the roots are. The roots are -2, so that's an x plus 2, and a +1, so that's an x minus 1. If I look at this, it looks like it's cutting straight through. So that's a multiplicity of 1 and a multiplicity of 1. And it goes up on both sides, so it's definitely a leading coefficient. I don't know exactly what that leading coefficient is, so I'll leave it as an A. But I do know that I have my roots and I have one other point. So I can figure out what a is. Because if I put 2 into my function, when x equals 2, f of x equals 5. So f of x equals 5 when x equals 2. 4 there and 1 there. So I have 5 equals 4a, or a equals 5 over 4. And so my formula is 5/4 times x plus 2 times x minus 1. Feel free to watch this video again, watch this part again, watch the other part again to see the steps, because I went through that quickly. All right. The other thing to keep in mind is here I used some random point, but often we'll use a vertex when it's a quadratic function. So if I have a function that looks like this, and I know that this point right there, which is going to be my vertex, is 2, 9. And let's say I know another piece of information. Let's say this point is -1 and that point is 3. So that's the point -1, 3 right there. Vertex form. And part of what you have to do is you have to recognize if I'm given the vertex, I want to write this as vertex form. If I'm given a maximum of my quadratic, I want to write it in max-min form. So I'll remind myself what that looks like. It looks like some leading coefficient times x minus h squared plus k, where h is the x coordinate and k is the y coordinate of the vertex. So in this case, it's going to be a times x minus 2 plus 9. And I have my vertex and I have one other point, so I can figure out that missing piece of information, because I know if I put -1 in, I get 3. So that means 3 should be a times -1 minus 2 squared plus 9. That happens to be 3 equals 9a plus 9. Subtract that over, -6 equals 9a. So a equals -2/3. So my formula is -2/3 times x minus 2 squared plus 9. This -2/3 makes sense because it opens down. And that's the end of 5.2.